This lesson is on reading scientific notation. The essential question here is, how can you read numbers that are written in scientific notation? So the key idea here is that scientific notation is a number that is written in scientific notation when it is represented as a product of a factor and a power of 10. The factor must be greater or equal to 1 and less than 10. So the factor is greater or equal to 1 and less than 10 is right here. So this number is going to be greater than 1 but less than 10. So there's only going to be one digit to the left of that decimal point. And then right here it's to a power of 10. And the power of 10 has an exponent. Now, when writing numbers in standard form, the absolute value of the exponent indicates how many places you move the decimal point. Now, you just got to remember, if the exponent is negative, you're going to move the decimal point to the left. But if the decimal point is positive, we're going to move the decimal point to the right. So, negative exponent to the left, positive exponent to the right. So when we're looking at this, trying to identify numbers written in scientific notation. So we're going to look at these different numbers and tell whether or not they're written in scientific notation. We have 5.9 times 10 to the negative 6. The factor is greater than or equal to 1, but it's also less than 10. And the power of 10 has an integer exponent. So the number is written in scientific notation. Well, how about B here? 0.9 times 10 to the 8th. This one would not be in scientific notation because the factor is less than 1. See, this number right here is 0.9. That is, remember, that number right there has to be greater than 1 but less than 10. And 0.9 is less than 1. I guess it should be less than or equal to or greater than or equal to. So the number is not written in scientific notation. Now let's look at these, writing numbers in standard form. So to write 3.22 times 10 to the negative 4th in standard form, we need to remember the exponent right here is negative, which means we're going to be moving the exponent to the left. So we're going to take that 3.2, you're going to take that decimal point and move it 1, 2, 3, 4 spots to the left, so we get 0.000322. Now, if we're looking at B here, 7.9 times 10 to the 5th, to write that in standard form, you're looking at the fact that the exponent is positive. Remember, when the exponent is positive, we're going to move the decimal point to the right 5 times, because it tells us right there how many times to move it. 5 times. So 7.9, you take that decimal point that was right there between the 7 and the 9, that point right there by the 7 and the 9, and you're going to move it 1, 2, 3, 4, 5 spots, so it's down here at the end. Right there is where your decimal point's now going to be. Now, how are we going to use that comparing numbers in scientific notation? Now, an object with a lesser density than water will float. An object with a greater density than water will sink. We're going to use each given density, which is given in kilograms per cubic meter, to explain what happens when you place a brick or an apple in water. So first off, we're going to look at 1.0 times 10 to the 3rd. Remember, the exponent is positive, so we're going to move that exponent to the right. So move that decimal point, to the right, the 3 units. So we're going to move 1, 2, 3, and we end up with 1,000. Now with the brick at 1.84 times 10 to the third, we're going to take that decimal point, move it 3 places, and we get 1,840. And for the apple, we have 6.41 times 10 to the second. It only has an exponent of 2, so we move the decimal 2 places, and we end up with 640. So when you're looking at these numbers, you're trying to compare what we've got. We've got 1,000 here, so this number is going to be greater than the 1,000, and this number is going to be less. So the brick will sink, but the apple will float, because the apple is less dense than the water, so it'll float. The brick is more dense, so it'll sink. Now let's look at a real-life application. In this one, a dog has 100 female fleas. How much blood do fleas consume per day? And it says over here, if we're looking, that the female flea consumes about 1.4 times 10 to the negative 5th liter of blood per day. So, first we need to figure out, we have 1.4 times 10 to the negative 5th times 100 fleas. So, first off, I'm going to remember that this is a negative exponent, so I'm going to move my decimal point to the left 5 spots. And we end up with 0.000014 times 100. So now that we've got it in standard form, we can multiply. When we multiply that, we end up with 0.0014. So what that means is that the fleas consume about 0.0014, or that would be 14 ten-thousandths of a liter, or 1.4 milliliters of blood per day. Go ahead and do your assignment on Clever, and make sure you bring up your notes to show me.